There we go. All right, today we're going to continue the fundamental theorem section. We'll do some basic ideas, and then we'll do part of a problem that was on an AP exam. I try to work those in as often as possible, just so you can kind of get more comfortable with what those look like for calculus. So here the idea is, can we construct a function? I don't know why I capitalized function with a given derivative and a value. Yes, maybe I was thinking this was a title. I don't know. So consider a function y equals f of x, whose derivative, dy dx, equals tangent x, so that f of 2 is equal to 7. So that's all given information. Using the fundamental theorem, we can start with, and this is where I did a bad thing partway through the problem. You're going to have to fix yours. Y is equal to the integral from a to x, where a is any constant, of, I should not use x again. I should use some other variable, typically t, but there's nothing magical about t. So this should be tangent of t dt. So that when we take the derivative of this, we get tangent of x. Right? So that was one of the qualifications. The other qualification was that f of 2 had to be 7. So what we can do is, if you remember, the integral from 2 to 2 of f of x dx, no matter what this function is going to be 0, right? We haven't gone anywhere. So what we can do is let a be equal to 2, so that we can do the integral from 2 to x of, again, let's fix this. So this is tangent of t dt. Plus 7. So now we've fulfilled both of the qualifications. The derivative of this thing is going to be tangent of x, because the derivative of the 7 is going to be 0. The derivative of a constant by itself is 0. And f of 2 will be the integral from 2 to 2 of tangent of t dt. That's 0. Plus 7 is 7. So we've done all the things that they have asked. Okay. So this is sometimes called an integral defined function, which is what we're talking about here. This is an integral defined function. It's a function that's not defined in terms of a polynomial or a rational function or a trig function or a logarithmic function or any of those other ones that you're familiar with. We've now defined the function in terms of an integral. Okay, you'll do a little bit of problems like this. That thinking is really important. What you'll see on the AP exam is sometimes where you have to think that way, but oftentimes you'll see problems like the one we're about to do. So let's take a look at that. So the graph of f shown below is continuous on the closed interval from a to b, from 0 to 8. I say closed interval and my mind immediately says a to b. Closed interval from 0 to 8 with horizontal tangents at x equals 3 and x equals 6. I don't know why it doesn't say and at x equals 1, because I'm pretty sure that at x equals 1 there's 1 also. Let's add that. X equals 1, x equals 3, and x equals 6. Then it defines this integral defined function. H of x is the integral from 1 to x of f of t dt. Okay? Then it'll ask you some questions. Typically on an AP exam they don't ask this many, but I'm asking some to kind of get you going. So first of all it says find h of 1. Okay, Well, h of 1, just applying the definition, is the integral from 1 to 1 of f of t dt. What is that? 0. All right, we didn't go anywhere. All right, next, is h of 0 positive or negative? Justify. That means write a sentence or two. Well, h of 0, again, using the definitions that they've given me, is the integral from 1 to 0 of f of t dt. We pretty much hate the fact that it goes from 1 to 0, right? We'd be much happier if it went from 0 to 1. Well, how can we accomplish that? Yeah, it's the opposite of the integral from 0 to 1 of f of t dt. Now, forgetting about this negative sign for just a second, the integral from 0 to 1 of f of t dt, is it positive or is it negative? Positive. The integral from 0 to 1 of f of t dt is greater than 0 because f is greater than 0 on the open interval from 0 to 1. We don't really care at the endpoints. You could make it closed at 0 if you want, but don't make it closed at 1 because it's not greater than 0 at 1. It's equal to 0 at 1. So, the integral from 1 to 0 of f of t dt has got to be less than 0. Because it's the opposite of the integral from 0 to 1. That makes sense? All right. What is the x-coordinate for which h has its maximum? Okay. So how do we find the maximum for any function? Forget about the fact that this is integral defined. How do we find the maximum? It has something to do with that, but that's woefully incomplete. But that's part of it. What is the name of the test that we use? We're going to use the candidates test, which we find the places where the derivative is 0 or undefined, and we also look at the endpoints. All right? So my candidates for this are going to be, where is h prime of x equal to 0? And this is where you use the fundamental theorem. I need to take the derivative of this integral defined function. What is h prime of x? No. If I asked you to take the derivative with respect to x of the integral from 1 to x of sine of t dt, what would that be? Apply that to this. Which would it be? It'd be f of x. All right, so where does that happen? At x is 1, x is 4, and x is 8, right? So those are some of my candidates. What is my other candidate? Yeah, x is 0. So we need to look at each one of those. So x of 0, is that positive or negative? Well, we already did that, didn't we? This happens not infrequently on AP exams where something that you have done in a previous part will help you with another part. So x of 0, clearly less than 0. What is, oh sorry, not x of 0, h of 0. My apologies. What is h of 1? We already did that also. What's h of 1? 0. What about h at 4? So that's just going to be the integral from 1 to 4. Well, you don't know a lot about it, but what do you know about it? Yeah, it's clearly greater than 0. And what about h at 8? So that's the integral from 1 to 8. That's going to be less than 0. Why? Under the, wait a minute, you keep saying under the graph?
Under the x-axis is greater than the area above the x-axis.
Exactly. There's more area below the x-axis than there is area above the x-axis. So that's negative also. So my answer is that x equals 4. All right. Now, what is the x-coordinate for which h has its minimum? Well, we've already done a lot of the work for that in part C. It's not at 4. We've already eliminated that. We have two places where our function h, oops, not there, is negative. Which one is going to be less?
H of 8.
Yeah, h of 8 is going to be less than h of 1. H of 1 is simply the opposite of this area here. That's a small negative number. Whereas h of 8 is the area from 1 to 4 minus the area from 4 to 8. Certainly appears to be quite a bit less. So that's going to be x is equal to 8. And then find the x-coordinate of each point of inflection of y is equal to h of x. All right, so now you got to pull that stuff back together. This is one of the things that the College Board is really good at doing, is asking a question which requires you to not only use what you are currently learning, but to use something you learned previously. They weave it all together. So, who can tell me about finding points of inflection? Where what? And when you say it, where? Which function? Like h of x. All right, so where h of x changes concavity. Exactly right. Well, we don't have a graph of h of x to look at, do we? The graph is f. Okay, so that's not the most helpful, but it's absolutely where we need to start. Well, notice h prime of x is, as we talked about earlier, f of x, right? And what's the definition of, for example, where h would be concave up? This is a definition I keep pleading for you to memorize. Where, who's it? I don't know what it is.
The derivative
Is,
positive. Right, yeah.
where the derivative is increasing. So where h prime is increasing, h will be concave up. Oh, okay. Well, h prime is f. So where f is increasing, h will be concave up. So here, h is concave up. Then it switches to, on this next interval, h is concave down. Here, h will be concave up. And over here, in that little interval there, h will be concave down. When the derivative of a function is decreasing, the function is concave down. When the derivative of a function is increasing, the original function is concave up. That's a super important definition that you just have to know. If you know it, it makes things a lot easier on these problems. So my points of inflection will simply be where we change concavity. So that'll be at x is equal to 1, x is equal to 3, and again at x is equal to 6. All the high and low points on the derivative of a function are points of inflection on the original function's graph, if that kind of helps you think about it. All right, so let's look at an AP problem. I picked this one, honestly, because it was one of the ugliest ones I could find. Okay, they are not all this hard, but some of them are. Was this on an AB? Oh, yep. AB, number 4. And you could almost smell the brain cells dying as students were taking this. So let's take a look. The continuous function f is defined on the interval from -4 to 3. The graph consists of 2 quarter circles and 1 line segment as shown in the figure above. So quarter circle, another quarter circle, and a line. Let g of x be equal to, oh, not just an integral defined function. Oh, no, that wouldn't be enough. They had to toss in this 2x here. So g of x is 2x plus the integral from 0 to x of f of t dt. Okay. So let's see what we can do with this. Find g of -3. Then find g prime of x and evaluate g prime of -3. That's 3 separate instructions. One of the things that I see sometimes with students doing these is because they're kind of hurrying, they kind of try to glom all this into one thing. It's 3 separate things they want you to do. Okay? Do them one at a time. Don't worry about the next one until you get to it. That's like days. Don't worry about tomorrow until you get to it. All right, so g of -3. By definition, that'll be 2 times -3 plus the integral from 0 to -3 of f of t dt. So that's going to be -6. And again, I don't like the fact that it's from 0 to -3. I'd be a lot happier if it was -3 to 0. Okay. So minus the integral from -3 to 0 of f of t dt. So it's going to be -6 plus, here's -3. So I'm going to have minus. How am I going to evaluate this integral?
greater than 4.
Yeah, this is going to be 1/4 of pi r squared. And what is the radius for that circle?
3.
3. So this is 1/4 of pi times 3 squared. And by the way, you really don't need to simplify that. There are a few stick in the muds at the AP reading every year, but most of the AP readers will be like, oh, smart student, why risk simplifying it? Nothing good can come of it. You don't get any more points for simplifying, and if you simplify it wrong, you lose points. Okay, so just leave it like that. All right, so now let's find g prime of x. Well, g prime of x, I'm just going to take the derivative of this function. What is that going to be? Perfect. 2 plus f of x. For the second part, we're just applying the second part of the first part of the fundamental theorem. So now we want g prime at 3. So that's 2 plus f at 3, which is negative 3.
G prime and negative 3.
Oh, my mistake. Thank you. So g prime at negative 3. So this will be 2 plus f at negative 3, which is 0. All right, so that's part A. Part B, determine the x-coordinate at which g has an absolute maximum on the interval from negative 4 to 3. Justify your answer. Okay, this is very much like the one we did a moment ago. We're finding an absolute maximum. We need to use the candidates test. So our candidates are going to be, well, whatever happens at negative 4. So we're going to consider, and most students don't write it in this language, but this is really what you're doing. We need to consider g of negative 4. We need to also consider g of 3, the other endpoint. And we need to figure out, well, where is g prime equal to 0? So I'm going to skip down a little bit and go, all right, so g prime of x equals 0 means that f of x has got to be what? Go back up to your definition.
2.
Try again. I want this to be 0.
Negative 2.
There we go. That's got to be negative 2. So where is this equal to negative 2? Well, it's somewhere in here. And this is the other part that torched some students, because they're like, and they absolutely freaked out at this point trying to figure out exactly where that was. The simplest thing to do, honestly, is to think about the equation for this line. Okay? The slope is just kind of ugly. You know, like, I don't know, is it 2.5? It feels like it probably is, but maybe it's not quite. Maybe it's 2 1/3. I'm really having trouble lining this up. Okay, let's write the equation for that line. So the slope, this goes down 6 and to the right 3, right? So the slope is negative 2. So my equation for that line is y is equal to negative 2x plus 3. And I want that to be equal to negative 2. So negative 2 is equal to negative 2x plus 3. Subtracting the 3, we get negative 5 is negative 2x. Dividing by negative 2, okay, it is 2.5. So the other place we're going to consider is g of 2.5. All right, so g of negative 4. Is going to be equal to 2 times negative 4. And I'm going to go ahead, and since I've already done this once, I'm going to change it to minus the integral from negative 4 to 0 of f of t dt. So that's going to be negative 8 minus, and I've got a piece that is below the axis. So since that's below the x-axis, it's going to be 1/4 of pi times 1 squared, but it's going to be negative. Plus the part above the axis. So that's going to be 1/4 of pi times 3 squared. And because we're going to compare this, I'm going to at least kind of make it this. I'm going to simplify it at least a little bit. That's going to be negative 8 minus negative pi over 4 plus 9 pi over 4. Let's see, that's 8 pi over 4, which is 2 pi. So it's negative 8 plus 2 pi. I need to consider g of 3. G of 3 will be 2 times 3 plus the integral from 0 to 3 of f of t dt. Well, that's going to be 6 plus, note the symmetry here. You've got this part above the axis and this part below the axis that are exactly the same size. So that's just going to be 6. And then g of 2.5 is going to be 2 times 2.5 plus the integral from 0 to 2.5 of f of t dt. That's going to be 5 plus, well, I've got this first triangle, and then the second triangle is not the same size, is it? The one that's below the x-axis. So the one above the axis, that's going to be 1/2. The base is 1.5, and the height is 3. Plus, oh, excuse me, minus, my fault, because the second part's below the axis, minus 1/2 of Well, let's see. That distance is 1 now, isn't it? Because we went from 1.5 to 2.5. And this height, we know that that's 2 because we were trying to find where our function was -2. So let's see. This whole part's going to be 1. So that's 4 plus 2.25 is 6.25. Ever so slightly more. So it's going to be x is equal to 2.5. All right, let's go on to part C. Find all values of x on the interval from -4 to 3. Notice it doesn't include the endpoints. It did that on purpose so you don't have to consider them. For which the function g has a point of inflection. Give a reason for your answer. Well, we know that g prime of x is equal to 2 plus f of x, right? So then g double prime of x is going to be f prime of x. So g has a point of inflection when g double prime equals f prime changes sign. When does f prime change sign? Right, I'm asking specifically, what x value?
Oh, x value? -3 and 1/2?
No, this is the graph of f. This is not the graph of f prime. What kind of values does f prime have here? And here?
Negative. Or positive.
F prime is this.
Oh, it's positive.
So it's at x equals 0. All right, and in the interest of time, we're not going to do this last part entirely, but it asks you to find the average rate of change. All of you know how to do that. Then it says there's no point in between the two endpoints where the derivative is equal to the average rate of change. Why does this statement not contradict the mean value theorem? Because this function, you can't use the mean value theorem on it. Because this function is not differentiable at x equals 0. So the mean value theorem doesn't apply to it. Okay, let's do the quiz.